Welcome! In this session, we're tackling an exciting string manipulation problem: reverse words in a string. This is a classic question that tests your understanding of strings, arrays, and efficient problem-solving techniques. Let's dive in and explore how to approach it step by step. In this problem, you're given an input string, s, and the goal is to reverse the order of the words within it. Here, a word is defined as any sequence of non-space characters, and words in the string are separated by at least one space. The task is to return a new string where the words appear in reverse order, joined by a single space. Additionally, the return string must be cleaned up to remove any leading or trailing spaces, as well as reduce any multiple spaces between words to just one. For example, if the input string is "the sky is blue," the output should be "blue as sky." Let's dive into the input and output formats to understand this better. For the input format, you'll be given a single string s. The output will also be a single string, but with the words reversed and properly formatted. Let's look at an example to illustrate this. For the input "the sky is blue," the output would be "blue as sky." Here, the words from the original string have been reversed, and there are no extra spaces in the output. Another example is the input string "hello world." In this case, the output would be "world hello." Notice how the leading and trailing spaces in the input are removed, and the words are reversed. Now consider a slightly different example, the input string "a good example." The output in this case would be "example gooda." This example demonstrates two important things. First, multiple spaces between words in the input are condensed into a single space in the output. Second, the words themselves are reversed while maintaining this improved spacing. Moving forward, the problem also comes with a set of constraints and edge cases that need to be handled to ensure the solution is robust. For constraints, the length of the input string s can be anywhere between 1 and 10,000 characters. The string will only contain English letters, digits, and spaces, with no special characters or punctuation. Additionally, there is always at least one word in the input. Some interesting edge cases to consider include strings with only one word, like hello, or strings with irregular spacing, such as leading spaces, trailing spaces, or even multiple spaces between words. Finally, an input string of maximum length, containing up to 10,000 characters, should also be handled efficiently. These scenarios ensure your solution works for a wide variety of inputs. To solve the problem of reversing words in a string, we first consider the brute force approach, which takes advantage of built-in functions like split, reverse, and join. The idea here is straightforward. By using the split function, we can convert the input string into a list of words, while automatically handling multiple spaces and trimming any unnecessary ones. Once we have the list of words, we simply reverse their order using a built-in reverse function, and then reassemble them into a single string using join, with a single space as the separator. This approach is efficient in terms of time, requiring n operations where n is the length of the string, as splitting and joining both take linear time. However, it does require n additional space for the intermediate list of words, which can be a drawback. While this method is simple and concise, it relies heavily on built-in utilities, providing less control over the underlying operations and increasing memory usage due to the intermediate data structures involved. To address the space inefficiency of the brute force approach, we can opt for an optimized strategy that focuses on in-place manipulation. The core idea here is to avoid creating intermediate lists by manually parsing the string. First, we trim any leading and trailing spaces from the string to clean it up. Then, we traverse the string character by character, extracting words while skipping any extra spaces between them. As we identify each word, we push it onto a stack to effectively reverse their order. Finally, we pop the words off the stack and construct the result string by appending them with a single space in between. This approach has the same time complexity of n, since we traverse the string twice, once to parse the words and once to build the result. However, it still requires n space for the stack. While this method provides more control and reduces reliance on built-in functions, it is slightly more complex to code and debug. Additionally, the stack still introduces some space overhead. Another alternative is the two-pointer approach, which uses minimal space by avoiding additional data structures like a stack. Here, we process the string in reverse, starting from the end and working backward to extract words. First, we skip any trailing spaces, then identify the start and end indices of each word. Once a word is located, we append it to the result string, ensuring that a single space separates the words except for the last one. After building the result, we trim any trailing spaces to finalize the output. This approach also has a time complexity of O(n), as each character is processed once, but it significantly reduces space complexity to O(1), apart from the result string itself. However, this method is more challenging to implement correctly, especially when handling edge cases such as multiple consecutive spaces or strings with no spaces. While it is the most space-efficient option, it demands careful implementation and is less intuitive compared to other methods. Each of these approaches comes with its own trade-offs. The split and reverse approach is fast and easy to implement, but it requires O(n) space for the intermediate list of words. The in-place manipulation approach improves space efficiency but increases the complexity of implementation, making it more prone to errors. Finally, the two-pointer approach is the most space-efficient, requiring only O(1) additional space, but it is harder to debug and implement due to its reliance on careful pointer management and edge case handling. Given the constraints of this problem, the split and reverse approach strikes the best balance between simplicity, performance, and readability. It minimizes the risk of bugs, leverages built-in functions effectively, and is practical for most scenarios, particularly in an interview setting where clarity and efficiency are key. To solve the problem of reversing words in a string, we need to address a few key points. First, the input string might contain leading or trailing spaces, or even multiple spaces between words. These need to be cleaned up to ensure the output is neat and correctly formatted. To do this, we can use built-in string manipulation functions like strip to remove unnecessary spaces from the beginning and end of the string. Once the string is cleaned, we split it into individual words using a space as the delimiter. For example, if the input is hello world, removing the extra spaces gives us hello world, and splitting it results in a list of words, hello world. Next, since the goal is to reverse the order of the words, we take this list and reverse its elements. Most programming languages provide efficient built-in methods to reverse lists, which makes this step straightforward. In our example, reversing hello world results in world hello. After reversing the list of words, the next step is to join them back together into a single string. This ensures the output matches the required format, with words separated by a single space. Using a join operation with a space as the delimiter, we can combine the words into a properly formatted string. For instance, joining world hello would result in the string world hello. Finally, this process string is returned as the result. It's important to note that breaking down the problem into these steps, cleaning the string, splitting it into words, reversing the list, and joining it back, is key to solving the problem efficiently. Additionally, handling edge cases is crucial. For example, if the input is just spaces like, pre-processing will trim it down to an empty string, which splits into an empty list and ultimately results in an empty output. Similarly, for inputs like ABC, the extra spaces are removed, and the reversed output becomes CBA. These steps ensure the solution is robust, efficient, and handles all scenarios gracefully. Breaking the problem into smaller components also highlights the importance of the data structures we use. Here, lists play a central role because they allow us to store the words after splitting the string and perform efficient operations like reversing and joining. The input and output are strings, but since strings are immutable in most programming languages, we use lists for intermediate processing. This design choice ensures the solution remains efficient and easy to implement. Speaking of efficiency, the time complexity of this approach is O(n), where n is the length of the input string. Splitting the string into words, reversing the list, and joining the words are all linear operations with respect to n. Similarly, the space complexity is also O(n), because we store the words in a list during the intermediate steps. This balance of time and space efficiency makes the brute force approach suitable for most practical inputs, while remaining straightforward to understand and implement. To better understand how this method works, let's walk through an example. Consider the input string, the sky is blue. First, we pre-process the string by removing the extra spaces, resulting in the sky is blue. Splitting this gives us the list of words, the sky is blue. Next, we reverse the list to get blue is sky, the. Finally, we join these words with a single space to produce the string blue as sky the, which is returned as the output. For an edge case like an input of just spaces, for example, pre-processing removes all spaces, leaving an empty string. Splitting this results in an empty list, which remains empty after reversing. Joining this empty list gives an empty string as the final output. These examples demonstrate how the algorithm handles both typical and edge cases effectively, ensuring the solution is both reliable and versatile. The solution to the LeetCode problem number 151, reverse words in a string, is implemented in a step-by-step manner to ensure correctness and robustness. ###line-by-line explanation. 1. The reverse words function begins by receiving a single input string s. This string may contain leading, trailing, or multiple spaces between words, so we need to handle it carefully. 2. In the first step, the input string s is split using the split function. By default, split breaks the string on whitespace and ignores extra spaces, effectively removing leading, trailing, or multiple intermediate spaces. The result is a list of words. 3. Next, the reverse method is applied to the list of words. This inverts the order of the elements in the list, effectively reversing the sequence of the words. Finally, the reversed list of words is joined back into a single string using .join words. Here, a single space is used as the delimiter to ensure the output string has exactly one space between each word, with no leading or trailing spaces. 5. The resulting string is then returned as the output. ####Key advantages of this approach. Efficiency: the solution operates in O(n) time complexity, where n is the length of the string. Splitting, reversing, and joining are all linear operations. Simplicity: the code is concise, leveraging Python's built-in string and list methods to handle most of the complexity. Edge case handling: the use of split inherently manages edge cases like multiple spaces, leading or trailing spaces, and empty input strings. For example, input, hello world-output, world hello. Input, empty string-output. This approach ensures the problem requirements are met with minimal and clean code. This is the Java implementation of LeetCode problem number 151, reverse words in a string. The logic mirrors the Python solution, where the input string is first split into words while ignoring extra spaces. The words are then reversed using Java's collections.reverse method on a list view of the array. Finally, the words are joined back into a single string using string.join. Unlike Python, Java requires explicit type declarations and uses utility methods from Java.util for operations like reversing and joining collections. To solve this problem, we start with an example where the input string contains extra spaces. The input is a string with multiple spaces, including at the beginning and end. The first step is to split the input string by spaces, which automatically removes any empty strings caused by extra spaces. This gives us a clean list of words. For instance, splitting the input "the sky is blue" results in the list "the sky is blue." Next, we reverse this list of words to reorder them from last to first. Initially, the list is "the sky is blue," and after reversing, it becomes "blue is sky the." Finally, we join these reversed words using a single space to create the output string. Joining the reversed list gives us the final result, "blue is sky the." This process handles the extra spaces efficiently, producing the desired output. Now, let's look at an example where the input string contains only a single word. The input here is hello. Again, the first step is to split the string by spaces. Since there are no extra spaces, splitting results in a list containing just one word, hello. Then, we reverse this list. However, reversing a single word list doesn't change its order, so the list remains as hello. Finally, joining the words with a single space gives us the same result, hello. This demonstrates that the solution gracefully handles single word inputs without altering the content unnecessarily. In this example, the input string consists entirely of spaces. When we split the input string by spaces, the result is an empty list, since there are no actual words in the string. With an empty list of words, reversing it has no effect, so the list remains empty. Finally, joining an empty list with a single space results in an empty string. This shows that the solution correctly handles cases where the input contains no meaningful content, returning an empty string as the output. From these examples, we can draw some key observations. First, the split function automatically ignores extra spaces, ensuring that only meaningful words are preserved. Second, reversing the list of words reorders them to achieve the desired output. Third, joining the words with a single space ensures proper formatting, regardless of irregular spacing in the input. Lastly, the solution effectively handles edge cases, such as empty strings, strings with only spaces, and single-word inputs, making it robust and reliable. By following these steps, we can confidently process any valid input string to produce the correct output. To analyze the time complexity of this solution, we start by looking at the first step, which is splitting the input string using the split method. This operation scans the entire string to identify words while removing extra spaces, making it proportional to the length of the string, or O(n). Next, we reverse the list of words using the reverse method. Since this operation adjusts the order of elements in place, its time complexity is proportional to the number of words, k. In the worst case, where the entire string is a single word with no spaces, k equals n, making this step O(n) as well. Both operations are linear so far. Now, for the final step, we join the reversed list of words into a single string using the join method. This involves iterating through the list and concatenating the words with spaces between them. The time complexity here depends on the total length of the output string, which is proportional to the length of the input string, or O(n). When we combine all three steps, splitting, reversing, and joining, each of them is O(n), so the overall time complexity for the solution is O(n). Moving to space complexity, the split operation creates a new list to store the words. Since this list size is proportional to the length of the input, its space complexity is also O(n). Additionally, the reverse method modifies the list of words in place, which means it doesn't require any extra memory. Its space complexity is O(1). However, when we use the join method to create the final string, a new string is allocated, and its size depends on the length of the input string. This step has a space complexity of O(n). Combining these observations, the dominant space usage comes from the list of words created during the split and the final output string, both of which require O(n) space. Therefore, the overall space complexity for this solution is O(n). To put this in perspective, let's compare this approach with a brute force or naive method. A naive solution might involve manually iterating through the string, identifying words, appending them to a new result structure, and reversing that result. This approach could require additional intermediate data structures and complex logic. For instance, repeatedly concatenating strings could lead to O(n²) time complexity due to the repeated copying of characters. In contrast, the optimized solution avoids such inefficiencies by leveraging Python's built-in operations like split, reverse, and join, each of which runs in linear time. As a result, the overall time complexity remains O(n), making it far more efficient. Finally, let's break down the time and space complexity across different cases. In the best-case scenario, where the input string contains only one word, the operations are trivial but still execute in O(n) time. For a typical input with multiple words, the time complexity remains linear since all operations scale with the string length. Even in the worst-case scenario, where the string is extremely large or contains no spaces, the solution's time complexity is still O(n). Mathematically, this is because each operation, splitting the string, reversing the list, and joining the words, iterates over the input or its components at most once. Adding these linear steps together results in O(n). Likewise, the space complexity is dominated by the list of words in the final output string, both of which are proportional to the input size, making the space complexity O(n) as well. When solving this problem, it's important to avoid common mistakes that can trip you up. One frequent error is confusing word reversal with character reversal. Remember, the goal is to reverse the order of words, not their individual characters. For instance, given the input hello world, the output should be world hello, not WLH. Another common mistake is failing to handle extra spaces properly. This means accounting for leading, trailing, or multiple spaces between words. For example, if the input is hello world, the correct output would be world hello with no extra spaces. Lastly, don't overlook edge cases. Inputs like an empty string, strings containing only spaces, or single-word strings must be accounted for. For example, inputs like comma or hello should result in comma and hello respectively. Accounting for these scenarios ensures your solution is robust and reliable. Another area where mistakes often occur is in the efficiency of string operations. Using inefficient techniques, like repeatedly concatenating strings in a loop, can lead to performance issues. This is because string concatenation often has O(n) complexity in many programming languages, which can be a bottleneck for large inputs. Instead, use efficient methods like Python's join or Java's string builder. Similarly, consider in-place modifications when allowed by problem constraints. In-place solutions reduce memory usage and are generally preferred in interviews, as they demonstrate an understanding of optimizing both time and space. To excel in interviews, it's important to understand potential variations of this problem. For instance, you might be asked to reverse words in place, preserve spaces between words, or handle punctuation like hello, world. Always communicate your assumptions clearly, for example, clarify how spaces, punctuation, and case sensitivity should be treated. Additionally, highlight the efficiency of your approach, such as achieving O(n) time complexity with O(1) extra space. Testing with edge cases is equally crucial. Be sure to verify your solution with inputs like empty strings, strings with only spaces, single-word strings, or those with irregular spacing, as these scenarios are often used to test the robustness of your solution. There are several related problems that can help you deepen your understanding of reversing words in a string. For instance, LeetCode 151, the core problem we're discussing, focuses on reversing words while handling extra spaces. LeetCode 186, on the other hand, introduces the challenge of solving this problem in place when the input is given as a character array. Moving beyond word order, LeetCode 344 is a simpler variation that focuses solely on reversing characters in a string. Finally, LeetCode 557 offers a twist by asking you to reverse the characters in each word while maintaining the word order. Exploring these variations can help you build a comprehensive skill set. Now let's look at some alternative approaches to solving this problem. The brute force approach involves splitting the string into words, reversing the list of words, and then joining them back together. While this method is simple and achieves a time complexity of O(n), it uses additional memory for the split and reversed list, which may not be ideal. A more efficient option is the in-place reversal using the two-pointer technique. This involves reversing the entire string first and then reversing each word individually. This approach achieves O(n) time complexity with O(1) space, but it can be more challenging to implement. Another option is using a deque, which allows efficient management of words while preserving their order. This approach is faster than list reversal in some languages but still uses extra space. Finally, there's the manual parsing approach, which avoids relying on built-in methods like split. Here, you iterate through the string manually to extract words and push them onto a stack. This approach has a time complexity of O(n) and a space complexity of O(n). While it avoids built-in methods and can be useful in certain scenarios, the trade-off is that the code can become verbose and harder to read. Each of these approaches has its strengths and trade-offs, and the best choice often depends on the specific constraints and requirements of the problem at hand. Great job! We've covered a solid approach to solving the reverse words in a string problem. Remember, mastering string manipulation is key to becoming a strong programmer. Keep practicing, and we'll see you in the next session. Don't forget to like and subscribe for more tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!